Welcome to Brain Vision.
Okay, so for this question, we can apply the energy balance equation, which is E dot in is equal to E out dot. And we know the rate of change of internal energy, kinetic energy, and potential energy is equal to 0 in this case. So therefore, we have m dot h1 is equal to m dot h2. As you can tell, m dot can cancel out, and this will give us h1 is equal to h2, which means that the enthalpy throughout the process is constant. Okay? And then if you take a look at the book, the back of the book, okay, which is the saturated R134a temperature table, you'll find out the enthalpies at temperature 25 degrees Celsius and the pressure 800 kilopascal is about 84.98 plus 87.83 minus 84.98 times 25 minus 24 and then over 26 minus 24. Okay, so the process here is the interpolation. So I do an interpolation here. This part is the temperature, and this part is the enthalpy part. So eventually we'll have the enthalpy for this case is equal to 86.405 kilojoule per kilogram. And then at temperature equal to negative 20 degrees Celsius, we'll have the enthalpy of formation is equal to 25.49 kilojoule per kilogram. And the specific enthalpy of a formation is equal to 212.91 kilojoule per kilogram. And the internal energy of a formation is equal to 25.39 kilojoule per kilogram. And the internal energy, the specific internal energy of the of vaporization is equal to 193.45 kilojoule per kilogram. And we know the 2 here just simply means that it's at the exit, okay? So based on all this information, so at temperature negative 20 degrees Celsius, the corresponding pressure is 132.82 kilopascal, which means that the pressure at the axis should be equal to 132.82 kilopascal. Now let's try to determine the quality at outlets, which is the quality at the axis, which is x2 here. So x2 can be equal to h2 minus hf2 over hfg. If we plug in the values, eventually we'll have 0.2861 as the quality of the outlets. So now we can plug in back to the equation for the internal energy of at the final state, okay, which is U2 equal to UF2 plus X2 times UFG2. So if we plug in the values based on the information with the blue letters here, so eventually we'll have the internal energy at the final state in this case is equal to 80.7 kilojoule per kilogram, okay? And these are the answers for this question.